Today, we're tackling a really big question for companies getting into Gen AI.
Hmm.
How do you get that amazing performance without, breaking the bank on specialized hardware like GPUs?
Exactly. It's this constant balancing act, speed versus cost. So we're diving into something called heterogeneous hybrid inference. Sounds complicated, but it's basically about being smart with your compute.
Using the right tool for the right job, essentially. Mixing CPUs and accelerators.
Precisely. And we've got some really interesting data to back this up. This isn't just theory. It really hinges on one key insight from looking at how people actually use chat AI. We looked at the LMSYS Chat1M dataset.
Okay, let's unpack that data point. What did you find?
Well, get this. About 75%, three-quarters, of real-world chat requests use fewer than 1,000 tokens.
75%.
Wow.
So most interactions aren't these huge, complex things we might imagine.
Not at all. They're relatively short. And that 75% figure, that's the key. It tells you what your workhorse can be.
Meaning the CPU.
Right. For a lot of typical chat use cases, your main goal, your service level objective or SLO, is getting a response back in under a second. That feels instant to a user.
Okay, under a second. So can standard CPUs, like Intel Xeons, actually hit that consistently for that bulk of traffic?
They absolutely can. We're talking 5th, 6th gen Intel Xeons here. They handle that 75% of short and medium requests pretty comfortably. We look at first token latency, TTFT, and for P50 requests, that's the median request, you're seeing TTFT around 0.56 seconds, well under that 1 second target.
Okay, 0.56 seconds for the median. That covers a lot of ground. But what about the rest, the other 25%?
Ah, yes. That's where things get interesting. That remaining chunk, say between 1,000 and 2,000 tokens, and especially the really long ones, the P90 to P99 stuff, those start to push past that 1 second latency goal on CPUs alone. User experience starts to suffer.
Right, so that's where the specialized hardware comes in, like Intel's Gaudi HPUs.
Exactly. You have to offload those demanding requests to something like an HPU. It's not just about meeting the SLO. It actually slashes the latency per token by like 3 or 4 times. And importantly, cuts the energy use by 2 to 3 times as well for those specific jobs.
Okay, so you've got CPUs handling the bulk, HPUs handling the tough stuff. But managing that mix sounds complex. How do you route the traffic correctly? Is there like a traffic cop?
Huh. Yeah, you need a smart traffic cop. That's where software like 𝗏𝗆AI runtime comes into the picture. It basically creates the single unified pool of resources from your different hardware types. Then it uses intelligent routing. It looks at the incoming requests, how long are they, how fast are they arriving, and it sends each request to the cheapest hardware that can actually meet that performance target, that SLO.
I see, so it's dynamically sorting requests?
Yeah.
Short ones to CPU, long ones to HPU?
Pretty much. Short, medium, long tiers, steered automatically.
All right, let's talk brass tacks. The economics. If you're sizing your CPU fleet just for that main 75%, what does that actually save a company compared to, say, an all-GPU setup?
The savings are, well, they're substantial. Your initial investment, the CapEx. We're seeing reductions around 90% compared to going all in on accelerators. 90% lower upfront cost.
90%, wow. And operating costs, OpEx.
Also a big drop. Because you're using those power-hungry accelerators much less, OpEx can go down by 50 to 70%. You're optimizing resource use.
And that ties into sustainability too, doesn't it? CPUs generally use less power.
Definitely. You know, a Xeon might draw 200, 350 watts and use standard cooling you probably already have. An HPU or high-end GPU is often 400 watts plus, needing more specialized cooling. So focusing on CPUs for the bulk means fewer watts per token overall, less e-waste, and you leverage servers you might already own. It's greener.
Okay, cost and energy make sense. But what about the output quality? Xeons are great, but often for models maybe up to 10 billion parameters.
Yeah.
How do you ensure the AI quality is still high?
That's a crucial question. You don't want to sacrifice accuracy just for cost.
Right. So how do you bridge that gap if you're using smaller models on CPUs?
This is where some clever software techniques come in, things that 𝗏 runtime enables. One key feature is high-density LoRa serving.
LoRa serving. What's that?
Think of LoRa adapters like little plug-in skill packs for the AI model. High-density serving means you can dynamically and automatically switch these adapters in and out really fast, tailoring the model for specific tasks on the fly. Combine that with other tricks, like something called test time scaling, and you can often narrow that quality gap significantly. You get surprisingly close to the big GPT-class models, even on cheaper hardware.
So you get the cost savings of CPU, but maintain competitive quality through smart software.
That's the goal. Enterprise-grade accuracy, snappy apps, remember that sub-second feel for most users, maybe 95% plus, but at a much, much lower infrastructure cost.
So, wrapping this up, the big takeaway seems to be smart tiering, intelligent routing. It lets you leverage existing CPUs for the majority of work, keeping accelerators for only the hardest tasks.
Exactly. You get performance where you need it and cost efficiency everywhere else. It makes powerful GenAI much more accessible.
Which leads to a final thought, perhaps. Could this democratization, this shift towards accessible CPU-centric inference, could that be a key to bridging the AI divide, making sure advanced AI isn't just stuck in a few giant data centers?
It's definitely something to think about, making AI practical beyond the hyperscalers.
Food for thought for your next deployment plan. Thanks for joining us on The Deep Dive.